Hi everyone, welcome back. Today we are going to discuss about the continuous functional calculus for self-adjoint operators. In the last lecture we have discussed the functional calculus for polynomials. So let us recall, let us take a self-adjoint operator T and P be a real polynomial. So that is, we can write P of t as a0 plus a1t plus a2t square plus so on plus an t power n, where these ages are real numbers, j equal to 0, 1, 2, so on n, an non-zero, and t is in the interval ab, closed interval ab, where a is less than or equal to mt and b is bigger than or equal to capital MT, where we know that t is nothing but integral a to b lambda dA lambda, and we know that P of t is nothing but a0 identity plus a1t plus a2t square, so on an t power n. Now using the representation of t and P of t, we can show that P of t can be written as integral a to b p lambda dA lambda. Okay, so let us call this as equation 1. Now the question we can ask is that, suppose we have a continuous function defined on the closed interval ab, how to define f of t? If f from closed interval ab into R is continuous, so how to define f of t? This is what we want to look at. In fact, we will answer this question. One obvious choice is that we can approximate f by sequence of polynomials uniformly. Now we know how to define polynomial of a self-adjoint operator. Using that, we will try to define what is f of t. Let us take, let Pn be a sequence of polynomials, of course real polynomials, such that Pn converges to f uniformly. Then we can define f of t as limit n tends to infinity Pn of t. But we know that Pn of t is nothing but limit n tends to infinity integral a to b Pn lambda dA lambda. This we already know. Now we can ask the question, can we say that this is equals to integral a to b limit Pn lambda dA lambda, and this in turn becomes equal to f of lambda dA lambda. Okay, so can we define in this way? So first let us try to establish the fact that f of t is well defined. That means if you have another sequence of polynomials qn which approximates f uniformly, then we should get the same limit. So let us take, so the first claim is f of t is well defined. Okay, so let us take, let Qn be another polynomial, another sequence of polynomials such that Qn converges to F uniformly. Now we should know whether Qn of t converges to F of t or not. So we have Pnt minus Qnt. This is nothing but, the first one is integral a to b Pn lambda d lambda, second one is integral a to b Qn lambda d lambda. So this is Pn minus Qn lambda d lambda. So this is we know that this is, so from this we can say that, so norm of Pnt minus Qnt. Now this is a polynomial in t, so that is less than or equal to norm of the polynomial. So in fact we can say that this is less than or equal to integral a to b mod Pn lambda minus Qn lambda d lambda. Okay, or we can actually write down this as, so this, therefore we can say that norm of Pnt minus Qnt is nothing but supremum modulus inner product Pnt minus Qnt acting on x, inner product with x, where x is coming from the unit sphere of H. So this is nothing but supreme of modulus integral a to b Pn lambda minus Qn lambda d e lambda x inner product with x. Okay, now this is less than or equal to norm of Pn minus Qn, supremum norm, and supremum norm x equal to 1 integral a to b d e lambda x inner product with x. But this is nothing but the identity operator, integral a to b d e lambda x inner product x is identity I of x inner product with x. So this is norm x square, so you will get norm Pn minus Qn. Okay, so this now we want to look at, hence we can actually write down norm of f of t minus Qnt. This is less than or equal to norm f of t minus Pnt plus norm of Pnt minus Qnt. Norm of f of t minus Pnt plus norm of Pn minus Qn subnorm. Now we know that Pn converges to F and Qn converges to F, so the second term goes to 0 and the first term anyway goes to 0 because Pnt converges to F of t in the operator norm. So as n tends to infinity, that means f of t also equals to limit Qnt. That means the definition of f of t does not depend on the sequence the sequence of polynomials that we are approximating f uniformly. Okay, so this is the definition of f of t. Now we can ask similar kind of question. What can we say about f of t? Is it, so let us look at, so we can say that f of t star equal to f of t all the time, because t is self adjoint. Now f of t is limit p and t. We know that each p and t is self adjoint. From that we can conclude that the limit is also self adjoint. So f of t is limit p and t, so where Pn converges to f in the uniform norm. Now from this we can conclude that since each Pn is self adjoint, f of t is also self adjoint. Next observation we can make about f of t is that we can say that norm of f of t is nothing but limit norm of p and t but we know that norm p and t is less than or equal to norm pn. So this is less than or equal to norm subnorm of pn, and pn converges to f uniformly, so norm pn converges to subnorm of f. Okay. Now the question we can ask is the following: can we say that f of t is nothing but integral a to b f lambda d lambda? In fact, this is true. We can prove using the polynomials again. So to prove this, let Pn be a sequence of polynomials in AB such that Pn converges to f uniformly as n tends to infinity. Let us take Pn such that Pn converges to f. Now we know that f of t is nothing but limit n tends to infinity p and t, and this convergence is in the operator norm. So we can so what we can claim is, we can claim that integral a to b f lambda d lambda minus p and t converges to 0, because we know that p and t converges to f of t. So from that we can conclude that f of t is nothing but integral a to b f lambda d lambda. Okay, let us look at so we have integral a to b f lambda d lambda minus p and t. P and t has the integral representation. We can write integral a to b p n lambda d lambda. So this is nothing but integral a to b f lambda minus p n lambda d lambda. Now we want to look at operator norm of this one. So consider operator norm of integral a to b f lambda minus p n lambda d lambda. Okay, now this is nothing but, this is supremum norm x equal to 1 integral a to b f lambda minus p n lambda d e lambda x inner product with x. This we have seen already. So this is okay, because we have seen that inner product dx with x is integral a to b lambda d lambda inner product x with x. This we have already seen. Now using this result we can conclude the above step. Okay, so we can say now on the right hand side of the above equation, this is Riemann-Stieltjes integral, because inner product a lambda x with x is positive. As lambda it is increasing, that means lambda going to inner product a lambda x with x is an increasing function. So that is a Riemann-Stieltjes integral. So the above quantity is less than or equal to supremum norm x less than norm x equal to 1 integral a to b mod f lambda minus pn lambda d inner e lambda x inner product with x. So this is less than or equal to norm f minus pn in the supremum norm multiplied by supremum norm x equal to 1 integral a to b d e lambda x inner product with x. But this is nothing but the identity operator only. So you will get supremum over norm x equal to 1 inner product x with x, that is norm x square. So on the right hand side you will get 1. So this is norm of subnorm of f minus pn. So but we know that this converges to 0 as n tends to infinity. So from this we can say that integral a to b f lambda d e lambda minus pnt goes to 0 as n going to infinity. But we know that pnt converges to f of t. So we can say that, so therefore f of t is integral a to b f lambda d lambda. So this functional calculus is known as continuous functional calculus for t. Okay. Now let us look at some other important properties of this continuous functional calculus. So we are looking at continuous functions in the closed interval a b and mapping these functions to elements of b of h as f going to f of t. So let us call this map as eta. So eta f is f of t. So we have shown that norm of eta f is nothing but norm of f of t is less than sup norm of f. Okay, now we can easily show that eta is linear. So we can easily check that eta of alpha f is alpha f of t is alpha times f of t, that is alpha into eta t. Similarly, we can show that eta of f plus g at t is nothing but f plus g of t. We can show that this is nothing but f of t plus g of t, that is eta f plus eta g. These two results we can use. We can approximate f and g by polynomials uniformly, and we can actually get the results. Now in the same way we can actually show that means eta is a linear map, and we can also show that eta of fg is nothing but eta f into eta g, that is fg acting on t is f of t into g of t. This is eta f into eta g. Again, this can be shown using the polynomials. You can approximate f by sequence of polynomials Pn and g by sequence of polynomials Qn. Now, using the definition of continuous functional calculus, we can get this result. As a corollary of the third one, suppose if f is positive on AB, then there exists f can be written as g square for some g positive on AB. Now we can actually by 3, so we can write f of t as g of t into g of t, that is g of t square, and we know that g of t is self adjoint. In fact, when g is a polynomial, we know that g of t is positive whenever g is positive, but here we have already shown that g of t is self adjoint, and g of t square is always positive. That means whenever f is positive on the closed interval AB, we can conclude that f of t is always positive. Now the question we can ask is that is the converse true? That means whenever f of t is positive, can we say that f is positive? Let be continuous function such that f of t is positive. Is it true that f is positive? In the case of polynomials, we were able to show that when t is self adjoint, p of t is positive if and only if p is positive on the spectrum. Now we can actually ask the same question. In fact, we can show this result to be true provided we prove the spectral mapping theorem for continuous functions. Okay. So these are some of the important results related to self adjoint operators. Okay. Now one more question we can ask here is that this map eta from CAB to B of H, f going to f of t, is it an isometry? So here we have not shown that it is an isometry. We have shown that it is a bounded linear map. In fact, it is also multiplicative. Instead of looking at the closed interval AB, if you just look at the spectrum of t, we can actually conclude that this map is isometry. So to do that, we need some more important information about spectral mapping theorem for continuous functions. So we will discuss those results in the coming class. I will stop here. Thank you very much.